Good afternoon, everyone. Thank you for joining me today. My name is Aditya V, Jonnalagadda, and I'm here to present my research on comprehensive and comparative analysis between transfer learning and custom-built VGG and CNN-SVM models for wildfire detection. This work is part of a broader effort to improve early detection of wildfires, which are one of the most destructive natural disasters. This presentation covers our approach where we compared custom-built models with pre-trained models using transfer learning, a technique that's gaining a lot of traction in the field of machine learning. In recent years, transfer learning has emerged as a central focus on artificial intelligence and machine learning research. The basic idea is simple but powerful. Take a model that's already been trained on a large general purpose dataset and fine-tune it for a specific task. This process allows us to reduce training times, improves performance, and use smaller datasets more efficiently. Instead of starting from scratch, transfer learning leverages the patterns and features learned by these pre-trained models, which helps to solve complex problems more effectively. Wildfires are a major natural disaster, causing extensive damage to forests, wildlife, and even human lives. Detecting them early is crucial, but it's also extremely challenging. Factors like lighting conditions, the time of the day, and diverse terrains make it difficult for traditional detection methods to be reliable. That's where AI and machine learning can step in. By training models to recognize wildfire patterns, we can detect fires at an early stage, allowing for quicker intervention and potentially saving lives and property. For this research, the main objective is to evaluate the effectiveness of transfer learning compared to models built from scratch. We used a dataset that stimulates real-world conditions like different lighting environments, times of the day, and a variety of terrains. Our goal was to see if transfer learning, with its ability to apply previously learned knowledge, could outperform custom models in wildfire detection, particularly when dealing with these challenging environmental factors. To conduct this study, we built 3 custom models from scratch: VGG7, VGG10, and CNN-SVM. These models were specifically designed for the task of wildfire detection. The VGG7 and the VGG10 are smaller versions of the standard VGG architecture, and they are customized to handle our dataset efficiently. The CNN-SVM model, on the other hand, combines convolutional neural networks with support vector machine classifier, which has been shown to be effective for image classification tasks. The goal here was to see how these models, which were designed specifically for wildfire detection, please keep that in mind, stack up against pre-trained models. In addition to the custom-built models, we also used 3 pre-trained models: VGG16, VGG19, and the ResNet 101. These models were originally trained on the ImageNet dataset, which contains millions of labeled images across thousands of object classes. By fine-tuning these models on our wildfire dataset, we wanted to see how well they could adapt to the specific features and complexities of wildfires, such as flames, smoke, and varying landscapes. The key advantage of these pre-trained models is that they already possess a lot of useful information about general visual features, which can be transferred to our specific task. Our dataset was made up of thousands of images classified into 2 categories: fire and non-fire. We used standard machine learning performance metrics like accuracy, precision, recall, and F1 score to evaluate the models. Both the custom-built models and the pre-trained models were trained and evaluated on this dataset. The goal was to see how well these models could generalize to unseen wildfire scenarios and how quickly they could detect fires under varying conditions. Now let's dive into the results. Our pre-trained models performed exceptionally well in the wildfire detection task. The standout was VGG16, achieving a near-perfect validation accuracy of 99.99% and an impressively low loss of 0.0056. This underscores the power of transfer learning and pre-trained models, which have the advantage of leveraging knowledge from a broader dataset like ImageNet and fine-tuning it for specific tasks. Whereas on the other side, custom-built models like VGG7 and VGG10 also performed remarkably well, with validation accuracies of 99.32% and 99.30% respectively. However, they had slightly higher loss values compared to VGG16, which suggests that while these models are strong, pre-trained models like VGG16 have a slight edge when it comes to generalizing to new data. Interestingly, ResNet 101, a highly regarded model in image classification, achieved a validation score of only 89.98% with a higher loss of 0.2526. This lower performance suggests that while ResNet is generally a very deep and powerful architecture, it may not be as suited to the nuances of wildfire detection in this particular dataset while detecting the features that are present for the wildfire. To further validate these models, we tested them on a set of 550 images with 325 fire instances and 225 non-fire instances. The results reinforced the superiority of VGG16, which detected 324 true positives with only 2 false positives and 1 false negative. This is an incredibly strong result, emphasizing the reliability of pre-trained models in identifying wildfires with minimal errors. In comparison, the custom-built CNN-SVM model showed a high recall rate, identifying 320 true positives but had more false positives compared to the pre-trained models. This suggests that while it's good at detecting actual fires, it may require further tuning to reduce false alarms. ResNet 101, despite being a highly regarded model, again identified only 301 true positives, which reflects its lower suitability for this specific task of wildfire detection. One of the key insights from our study is that both the custom-built and pre-trained models performed very well, with only minor differences in accuracy. While pre-trained models like VGG16 and VGG19 showed slightly better results. Custom-built models like VGG7 and VGG10 were still highly accurate, making them strong candidates for wildfire detection. A key advantage of custom-built models is that they are less deeper in the sense of a neural network than pre-trained neural networks, meaning they require less computational power. This makes them highly useful for inference on devices with low capacity GPUs and CPUs, where efficiency and speed are critical. In real time wildfire detection applications, custom-built models offer a good trade-off between performance and computational efficiency. On the other hand, pre-trained models tend to excel in more general-purpose detection tasks. Because they have been trained on a wide range of objects from datasets like ImageNet, they are better equipped to handle diverse environments and conditions. For example, in a forest during the fall season, the terrain may change due to different foliage, or environmental factors like fog or mist could obscure visibility. Pre-trained models, having been exposed to a wider range of object classes, are more robust in these scenarios. They can even handle the presence of human-made objects like watchtowers or fences, reducing false positives in complex environments where a custom-built model would fail. In essence, custom-built models are ideal for resource-constrained systems, while pre-trained models shine in environments where varied terrain and conditions are a factor. In conclusion, transfer learning has proven to be a highly effective approach for wildfire detection. Pre-trained models like VGG16 and VGG19 significantly outperformed custom-built models in terms of accuracy and precision. However, the custom-built models offered faster computation, making them more suitable for real-time applications. Moving forward, we plan to explore hybrid models that combine the strength of both approaches. Additionally, we aim to focus on fine-tuning these pre-trained models to better handle dynamic wildfire scenarios such as changing weather conditions or rapidly shifting landscapes, and the same also applies to the custom-built models. Here I'd like to take a moment to acknowledge the contributions of my co-researchers and my professors, who were also my guides, and the funding support from the National Sciences and Engineering Research Council of Canada, which made this work possible. With that, I'd like to thank you all for your attention, and I'm happy to answer any questions you may have. Thank you very much and have a nice day.